Well, hi everybody. Thanks for having me here. This is one of those kind of rare occurrences where my personal passions and my professional life kind of come together nicely. In my sort of non-work life, it's weird saying that, but I sort of have a small NGO where I help countries that don't really have the resources that we're lucky to have here in the U.S. Develop open source solutions and innovative technologies like thermal cameras or drones for anti-poaching enforcement, or telemetry for animal movement studies for their management needs. But in my professional life, I work for the U.S. Department of Interior, and the agency is under the Department of Interior is the Bureau of Ocean Energy Management, or BOEM. And we have our agency is responsible for the water's offshore energy, so renewable energy, non-renewable energy, and mineral mining in the waters of the United States, and what's known as federal waters, and or the Outer Continental Shelf. To be able to do that responsibly, you need to have a pretty extensive understanding of animal movement and behavior. So let's see. I just want to make sure this. There we go. Just want to advance my. Can you guys? Oh, hold on. I'm not. Oh, there we go. All right. So animal telemetry is a really important part of my job, but not just my job and my agency. It's across government agencies. So if you work at the U.S. Fish and Wildlife Service, you might have an interest on where terrestrial species go, or even some freshwater fish or sea turtles, depending on where you are. If you work at the National Park Service, you have an interest in telemetry. If you work at NOAA, you have an interest in telemetry. The Navy, all across the federal government, we rely on telemetry from animals for one reason or another. In my case, it's for looking at ocean animal habitat use. This is an example from I believe it's a pilot whale study or melon-headed whale study in Hawaii that looks at sort of core residence areas. And we were primarily interested in identifying foraging habitat and looking at fine-scale behavior as well in terms of how animals are using a habitat, not just for location, but what are they physically doing there. So this is done across species. So we do things on birds, and we do things underwater, both on animals that breathe air, like the sea turtle, but also on animals that don't, where we might use an archival tag, like on a sturgeon or a shark or a tuna or something. So across the agency, we have a lot of different uses for telemetry. Increasingly, as I'm sure you guys are aware, telemetry is sort of becoming a way to sort of do more than just study animals. We can start to, there are groups like at St. Andrews that are putting all sorts of sensors on satellite tags that are able to tell us about the environment around them, with the water quality, the salinity, and all sorts of other stuff about the water around them. So as sensors get smaller, we're able to do more and more, get more and more out of these, not just about the animals, but about the environment they're going into. And so imagine if we could have a network of these sort of oceanographic gliders, only the gliders are sort of animals, and those animals are telling us about the environment all around them all the time. But as we get, as tags increase, the data the way we get data off them has not really changed much. This is sort of a joke. This is a screenshot from the Jaws movie. But the way we, while tags have changed dramatically, the technology that we use in space for tracking animals, with the exception of ICARUS recently, really hasn't advanced much. And so when I started looking into this, I started asking questions about, why are things like Argos so limited? Argos is just a handful of satellites. And if you're looking at something like a sea turtle, again, my work focuses primarily underwater. That turtle is only going to surface for a few seconds when it takes a breath, and then there's no chance of getting another satellite signal from that animal. And unless you have an acoustic array following it, you're not going to be able to use other types of tags either. So this means that there's a significant chance of error rates with Argos. In fact, If you satellite tagged a leatherback turtle in southern Florida or the Caribbean, it would only have about 10 or 11 minutes of satellite coverage. So those satellites are only overhead for 10 or 11 minutes of every hour. So that means an animal that dives for an hour or more to thousands of feet would need to come up, take a breath when there's, and arch its back so that tag can fire off a signal, and the Argos satellites are overhead. So the numbers don't work out well. And the result is you can get significant error codes. Error codes on the Argos system are based on how they're able to the signal quality that each satellite can get and how many satellites get that. And as that satellite gets closer to the horizon, the larger that error rate can become. So when you're dealing with ocean animals, there are a lot of things that are working against you. They're coming up for very, very brief periods of time, if at all. There's limited satellite coverage, but yet we're increasing. The technology has gotten really amazing with all these sensors that they're able to carry. So I started putting some queries out there and ended up contacting my friends at NASA to find out how we could change this. So this is, I already started going into this, but you know, this is just a map of one of the ways that we use telemetry data. These are walruses in Alaska, and you don't want to see that any energy development happening up there, impacting endangered species or protected species like walrus. There's also the native Inuit communities that you don't want to impact. They rely on walrus and polar bear hunting and bowhead whale hunting. So you need to take into account their needs. These are people that, you know, you can't go to the grocery store in Point Hope, Alaska. And the subsistence communities have been doing this for generations. So there's a lot of factors to take into account, and animal movement plays an important role there. But the Argos system, really, we have sort of an old school satellite technology. The space industry has changed dramatically over the past decade, and I'll tell you a little bit more about that. And there's limited geographic coverage, and this means that we've got a scenario that I thought, and the folks at NASA and folks in the private industry think is pretty ripe for disruption. So currently, Argos has a number of, you can either have a ground station or a handful of satellites in orbit. The data, your animal comes up, it sends data to the satellites or your ground station if you happen to have one nearby and the animal happens to be by it. And the data goes, and it goes to a data processing center, and you can access your data online. What we're looking at is how to change that, and looking at just shifting the paradigm of having a common communications frequency across airborne assets and across ocean assets and space assets. So if you think about the two presentations we've seen prior, it talked about UHF, it talked about VHF, it talked about Argos, it talked about GPS, but it's not on a common communications frequency, so that we can't shift, we can't leverage technology that's used in one area for another. We can't, we can't supplement Argos because, well, we can if we were to do more stuff with these ground stations, but they're sort of cost prohibitive. And so what we started thinking about was, well, what if we have a common communications frequency across Argos, across the micro small satellite community, even on weather balloons, experimental aircraft, get everyone together on the same page so that we can reduce the location inaccuracies of Argos and increase the data pipeline of data that's coming off it. So those were the two objectives in the study that I set out to, that we're in the middle of doing with NASA. And so our goal is to, again, increase the location quality that comes off of Argos. And these are Argos tags that are just using Doppler effect for locations because they're the lowest cost and easiest to get in larger mass. And also not be limited to the data bandwidth limitations of Argos. You know, it's kind of crazy that my parents watched the moon landing live on TV, but my sea turtles in the Gulf of Mexico only get a few minutes of every hour for a few kilobytes of data. There's got to be a better way. And I'm not an engineer, but luckily I was able to connect with a lot of NASA engineers to help us sort of chart this path. So we have sort of a two-pronged strategy that we're in the middle of doing now. And so we have a lot of internal engineering expertise at NASA and also leveraging crowdsourcing. The internal engineering expertise is doing a lot of signal characterization. This is unfortunately the only picture I was able to get of a recent near-space balloon launch that we did a few weeks ago, where we basically took a Argos ground receiver to see how it would function in near-space conditions. So you submit it to that microgravity, you submit it to, subject it to the thermal stresses and the winds and all that stuff. Things that we obviously put the Argos receiver through all sorts of tests in vacuum machines on land, but ultimately you need to go pretty close to space to get those kind of conditions. And then we drove around the countryside of the Pacific Northwest with satellite tags, and we're able to characterize the signal that receiver received. And while we haven't published the final analysis yet, this is certainly one potential feasible approach, is having a common open source receiver without changing tags. What we don't want to do is dictate frequencies that tag manufacturers have to use or anything like that. We want to be able to leverage existing technology and then make the jump to how we can improve things for the future. On the crowdsourcing side of things, looks like part of my slide got cut off there. That should say challenge. We just wrapped up, it just closed a few days ago, a crowdsourcing challenge that was meant to sort of bridge the gaps between some of the data science community and the engineering and the animal telemetry community. And there's going to be $30,000 in prizes. We had 434 people participate in the challenge. 36 proposals came in. Of those, we've got about 20, I think, that are worth a very close look for the competition. And it's what's considered an ideation challenge. Describe to us how this larger vision would work. And what are the sort of the legal hurdles, what are the engineering hurdles, and how could those hypothetically get overcome? And so that's what NASA does for big picture, it's called an ideation challenge for getting some of these bigger picture visions together. This was the first time my agency, BOEM, has ever done anything like this. So it was very cool to be able to leverage NASA's Tournament Lab expertise and their Advanced Exploration Systems division into something that would benefit animal telemetry. It was a very cool experience. We had participants from all over the world. So the challenge, the nice thing about doing these crowdsourcing challenges is it's not limited to just the United States or people that follow Jake on Twitter. We had people from, I believe it was 25 countries around the world that were participating, and sometimes teams composed of people from multiple countries. The nice thing about the forum is, if you're someone that has engineering skills and there's someone that has animal telemetry experience, people would connect that way, and proposals would come together. But we're in the middle of reviewing those proposals now, so we hope to announce a winner or multiple winners by December 10th. So the question is really, where do we go from here? So like I said, we've got a winner being announced December 10th. And it's likely that we're going to have a second or third challenge. It depends on budget and all that stuff too. But the idea is you start off with this larger ideation challenge with getting that bigger vision more clearly defined, and then we can sort of chomp up smaller pieces of the puzzle. So we can get to okay, what is one aspect of, say, telemetry from low Earth orbit to ground stations, and then from ground stations to the scientists. We're going to have other challenges that are more focused on specific elements of how this could get implemented. A key requirement in the challenge is feasibility. So you can't tell me, hey, train all elephants to listen for wolves, and when they hear a wolf, tell the other elephant, and somehow that gets back to Jake. It had to be grounded in reality and things that are actually feasible. And then we're continuing to test on the NASA engineering side open source receivers. So there are a number of companies that are now making software controlled radios. So what that means is you're able to set a radio on board your satellite or your microsatellite to listen for a specific frequency and then transmit that back. There are regulations, so you have to stick to regulations when you're transmitting, but for listening, there really aren't any rules. Anybody can listen to an Argos signal. So the idea is that you've got, we're forecasting, the U.S. Air Force has a space tracking command that tracks all the orbital, the debris and all the satellites and everything from everyone in orbit. And I'm sure they track stuff that they don't tell us about too, but the idea is that they're forecasting about 18,000 small satellites to be in orbit over the next 5 to 10 years. And there was just in the news the other day that the Federal Communications Commission here in the US approved SpaceX for 7,000 satellites, small microsatellites to go in orbit to provide broadband internet. So my vision is that we can get all these on the same open source receiver that all of them have the same software defined radio package, and we have 18,000 assets rather than a half dozen or a dozen Argos satellites that can all help improve location quality and open up the data bandwidth of what we can get off satellite. So at the end of this, that's a big vision that's far off. There are some interim steps. For example, NASA has what's called the CubeSat Launch Initiative, which is basically whenever you hear about the International Space Station being resupplied or satellites going up just on launches, those satellites all are able to have extra space for hitchhikers to come on board, namely these small microsatellites, these CubeSats that are about about the size of a coffee mug. After they unload their gear and take their garbage off the International Space Station, these resupply modules go up about another 250, 300 kilometers above the space station and then launch a bunch of these small satellites. The vision with NASA is that as part of this CubeSat launch initiative, if your university, of which there are I think about 100 or so participants, if your university includes sort of an animal tracking payload, you will get not just a free ride to orbit, which is a huge deal, but you will get moved to the front of the list. So there's quite a long waiting period to launch a satellite in orbit, and so they're pretty valuable things. And obviously, for-profit companies are buying up all the launches they can. So through NASA's CubeSat Launch Initiative, universities can get moved to the front of the line if they carry a receiver for this animal tracking initiative. So that's basically my project here in a nutshell.